Hey, it's Tony from Adafruit, and in this video we're going to look at the MPR121 Capacitive Touch Sensing Breakout Board and how to use it with CircuitPython. So the MPR121 is a nice little board like this. Basically is a little chip that can detect when any of these 12 inputs at the top up here are touched. So if you touch them with your finger, it detects the change in capacitance, and then you can read that in your Python code to see if someone touched something. And the cool thing is these pins, it can detect the touch, but if you connect something to those pins that's also conductive, like a wire, a piece of aluminum foil, or even something that's like mildly conductive, like a piece of fruit, or, I don't know, just any kind of like semi-metallic thing, piece of plastic that doesn't conduct anything might not work. But it can detect that change in capacitance, so when you touch that object that's connected to the pin, then you can detect that in your code and do something. So we'll look at a couple demos, and I have a fun one towards the end here. You see I have this crazy setup that we're going to come back to over here. I'm going to play the electric spoons, hopefully at the end of this video. So I'll walk through this video how to use a little library that I wrote to use this with CircuitPython. And again, be careful, this right now the library works with CircuitPython. There's some small differences, so it doesn't work with MicroPython right now, but in the future we'll probably have a shim layer that'll let you use this with MicroPython pretty easily. But it's easy to use. Like, for example, if you have the ESP8266, you can load it up with the MicroPython, or the CircuitPython firmware rather, and then use this library right now for it. So let's just kind of dive in. And I'd done a previous video on this where I was just investigating capacitive touch, and I wrote the start of this library. And so now in this video, we're going to look at the actual final library and look at a couple demos for it. So this video is just going to be how to install the library and how to run a couple demos for this. And if you saw last week, I had started a little series on some neat NeoPixel animation stuff. We'll come back to that probably next week. I wanted to just do another quick little video on this MPR this week. So let's go to the main view and get started here. Jump into the desktop view. Okay, so to go along with this, I have a nice tutorial that's in the Learn system, and I'll put a link on the description when this goes up on YouTube. So look down below, you'll see a link to any of the web pages that I mentioned right here, links to the products and things that I'm talking about here also. But take a look at this guide, and this will walk you through how to install the little module that you need to use this with CircuitPython. And again, this is the little breakout board right here, like I showed before, the MPR121. There's also an Arduino Shield version of this, so that would work well if you have like an Arduino Zero that's loaded with the CircuitPython firmware. And so in the first page of the guide just talks about what this is. It's a capacitive touch sensing breakout board. So there are 12 different inputs that it can detect capacitive touch sensing. So that just means, like when you're human, when your body touches something, that changes the capacitance of what you're touching because there's a larger surface area for the electrons to flow around, and then that changes the capacitance, and these chips can detect that very slight change. It's a really small change, but if the chip is able to look for that tiny change, then it can detect that. And the nice thing is it has an I2C interface, so just 2 wires effectively. You also need a power and a ground, so 4 wires really. But with a few wires, it's a digital protocol, so you can send a command to this chip that says, hey, what inputs have been touched, and it'll return back exactly what inputs have been detected. Because you can do capacitive touch sensing without using a breakout board like this. But there's some tricks to it. You can do it in Arduino if you use the capacitive touch sensing library that Paul Stoffergen wrote. Really nice library. Doesn't work in CircuitPython right now because you need to do some exact timing things. I don't even think it works in MicroPython. But there's potential maybe in the future to do this without some of these boards. But the nice thing about this MPR is it's relatively inexpensive, like $8 it looks like is the cost of the breakout, and you get 12 different inputs, so it's a lot more inputs than you would typically have on an Arduino. It's pretty bulletproof. You can use it with the Raspberry Pi also. Pretty much any I2C device should be able to talk to it. Okay, so let's jump into the hardware page. This talks about what you need to follow this guide. So obviously you need a board that's running CircuitPython. I have right here a little Feather. This is the Feather M0 Adalogger version, but really any M0 Feather would work. That's because I have loaded on it the SAMD21 port of CircuitPython. You could also use the ESP8266, but again, just make sure that your board supports the I2C interface, and pretty much every board supports it as far as I know. But the ESP8266 or the Feather M0 are good options for this, or the Arduino Zero would also work for this. And then make sure to load CircuitPython onto the board. And so I have a link to a guide right here that'll tell you how to do that. And then you obviously need the MPR121 capacitive touch sensing breakout. So you can get the breakout version, or there's an Arduino Shield version right here, which is kind of handy. The Arduino Shield version is nice in that it has really big holes that you can put alligator clips on easily. So if you're making a neat demo, like you see these spoons over here, like I said, we're going to come back to these. I'm going to keep you in suspense over these spoons. But if you want to connect alligator clips like I have right here, the Shield version is really nice because it's easy to connect them. The breakout's fine. I just have to have little wires that kind of jump out and then connect to those. You'll want breadboard, hookup wires, and soldering tools because you need to solder some headers onto this breakout board. Really easy soldering job though, even if you're a beginner and you haven't done a lot of soldering. Check out this guide to Excellent Soldering. It'll tell you how to make a good solder connection, and just practice a little bit. Practice makes perfect. This is a good thing to practice on because it's only, you know, maybe about 18 or so pins to solder on, and it's even though it might seem hard as a beginner sometimes to do soldering, it's hard to screw up soldering headers. It is possible. I've done it. Every beginner will do it, but don't feel so bad. It's not as difficult as you might think. Alligator clips, these are really handy, like alligator clip wires. These are these wires that you see right here. They have these nice little ends that can snap on and grip something, you know, like an alligator. So that's kind of nice because I have them connected to conductive things like these spoons right here. And like I said, that we can detect that capacitance change when I touch a spoon right here because it's connected to the alligator clip, and then we're eventually going to connect that to the MPR board right here. We'll be able to detect that change. And so alligator clips are really easy ways to connect things without having to like permanently solder them together. So, okay, so that's what we need to follow this. And then you'll also first want to follow the MPR121 guide. This tells you how to assemble the breakout, which is really simple. You just have to solder these headers onto it. But it's good to go through that guide and just familiarize yourself with it. Also, to test it out with Arduino, you know, that's a good thing to try. It just, you know, even if you're not going to write your code in Arduino, in the guides that explain how most of the breakouts work, they usually link to the Arduino library. So try that out first just to make sure that, you know, you can see the device working, because CircuitPython, MicroPython is still kind of a new thing, and so it's hard to troubleshoot when something goes wrong. Is it a problem with CircuitPython? Is it a problem with the hardware? Is it a problem, you know, with how it was assembled? So, you know, remove as many variables as you can and start with the Arduino version. Make sure you see that working, and then move on to the MicroPython or the CircuitPython version would be my suggestion. Now, to wire this up, it's really easy. So I've got the breakout right here. I've got my feather board. Basically, I need to connect the ground connections. So on the breakout, there's a GND, a ground connection. I'm going to connect that to ground on my feather board, which is right here. Yeah, the fourth pin over. And then a power connection I need to make. So I'm going to connect the VIN, the voltage input line of the breakout board, to the 3 volt or 3.3 volt power output of the feather board right here. And it might be a little hard to see. I can't really move this into the view of the camera, but this diagram right here is exactly what I'm following. So that's all that I'm doing to wire this up. And then the serial interface. So it's an I2C interface. So I want to connect the SDA connection, and this one on my breakout is a little bit loose, so I want to make sure that I get a good connection. There we go. So that, oops, oh, see, I just pulled it right out. So SDA to SDA on the breakout board, which is right there. And then the SCL, or the I2C clock line, which is right next to it on the feather. Connect that to the SCL line on the breakout board, which is right next to it right there. Okay, cool. So that's all set. And just make sure I get a good connection on there. Okay, so that's all you need to do to wire this up. Like I said, it's easy. It's just 4 wires. Other devices can share the I2C bus. It's pretty convenient like that. So, okay, let's go to the software page now. And this is also relatively straightforward. So we need to install a module to talk to this board. And it'll give us a nice Python interface for talking to the MPR121 sensor. Now to do this, I have a bunch of text right here. So again, make sure you're running CircuitPython and not MicroPython. So there's a difference here. And right now the library only works with CircuitPython. In the future that might change, and it'll probably eventually work with all the versions. And let's see, so what you want to do is you need to go to this module on GitHub. So this is where the code for this module is located. And you want to go to the release tab, and under the release tab, look for the most recent release. and then you should see this zip file, Adafruit MPR121.zip. So you want to download that file and open it up, and inside of there will be a directory, an Adafruit MPR121 directory. And then inside of that directory will be some files, but we need to copy that directory onto our MicroPython board's file system. And if you go back to the guide, that's what it explains right here in this all this text right here. Now there's actually another library that we also need to copy over. So this paragraph talks about there's this bus device module or library. And so just like with MPR121, go to the releases tab, grab the latest zip file from the latest release, download it, unpack it, you'll find a directory. It should be the same name as the zip file, Adafruit_bus_device. And then you also want to copy that directory to your MicroPython board. So on your MicroPython board, there should be both the Adafruit_bus_device directory that you downloaded from the zip file, and then also the Adafruit_MPR121 directory that you downloaded from this zip file. And so this part of the guide kind of explains that and shows it. The nice thing with CircuitPython on the SAMD21 processors is that it shows up as a little drive. And so you can see here's my CircuitPython board, and I have both these directories already copied over onto here. If you're using like the ESP8266, you can use a tool like Ampy to do that. And so I linked to a guide that explains how to copy a file onto your board using a tool like Ampy. So get those two directories onto your board, and then we're ready to start playing with some of the code. So in the module code on GitHub, there's an examples folder. And so let's look at the simpletest.py example. So this is like a really basic example of how to use the code for this module. So, and I won't even maybe use this yet. Like I'll just go through the serial REPL first, and then maybe we'll take a quick look at this code, and then we'll look at another more interesting demo that I have here. So let's open up the serial terminal for my MicroPython board. So I'm going to use the screen command, and this is just going to open the serial terminal on the board right here. And then if I press Control C or Control D, there we go. I just want to make sure I reset the board. Oops, I'm in this raw mode. There we go, press Control B. This is just because sometimes when you're using Ampy commands, it will leave the board in this raw REPL mode. And so if you open the REPL and you don't see anything and you're pressing enter and like nothing's happening, try pressing Control B, B as in boy. That will exit the raw REPL mode. You can see right here, raw REPL, Control B to exit. And then try Control D after that. Control D as in dog. So that will do a soft reset. Basically, you know, if you're not getting anything, try both Control B and then Control D to just go out of this raw mode, do a reset of the board, get you back into a known state like this. And if all that else fails, exit out of your terminal, unplug the board and plug it back in, and then reconnect to it, and that should get it back into a good known starting state. Okay, so to use this module, first I need to import the board module because that gives me access to all the pins. And then next I need to set up the I2C bus, and this differs between ESP8266 and SAMD21 MicroPython. If you look at the simple test example, it actually has a little block right here that says, here's what you want to do, or rather this block right here, you want to uncomment one of these lines of code right here, either import native IO as IO or import bitbang IO as IO. This is just dealing with the differences in that the ESP8266 has a software I2C interface, whereas the SAMD21 has a native hardware I2C interface. And so you need to be explicit about telling it which interface that you want to use right here. So since I'm using the SAMD21, I'm going to import native IO as IO. So this just renames the module after it's imported. Gives it a nice little consistent name that I can use across both of those. Okay, and then I want to import the Adafruit_MPR121 module. So that imports the module. And then now that I've got all my imports done, I want to initialize the I2C bus. So I do that by creating an I2C device, and that's in the IO module I2C. I need to pass it in the clock pin and then the data pin. So I can say the board.scl pin and then the board.sda pin in this case. So that's all good. And then just as a sanity check, I like to call I2C.scan. This will do a quick scan and just tell me what devices are connected to the I2C bus. So this gives me the address of the device that it finds. So it found a device with address 90. That's in decimal, it's not in hex. So that's good. So it sees that there's a device on the bus. That means my connections are good and that I'm able to see this chip and that very likely the library should work. If I didn't see anything, if I just saw an empty array like that, that would be bad, and that probably means that I might not have like a power or a ground connection connected correctly, or maybe my serial clock or data lines aren't connected correctly. So just double check all those connections. Check like the soldering for the headers, make sure it's a good solid connection, and then try that scan again until you see the device. Okay, so the next thing I want to do is create an instance of this MPR121 class. So this is pretty straightforward. We'll say MPR121 equals, from the Adafruit MPR121 module, the MPR121 class. And then this just takes in by default that I2C bus that I created ahead of time. You can also change the I2C address by passing in an optional parameter right here. Like if I wanted to change the address, I could specify it like this. But I'm just going to use the default address because I haven't changed it on this board. There is an address pin. I think you can change it to like one of two address values. But in most cases, you're going to use the default. So I do that. And at this point, I'm ready to start using this module. So it's pretty simple. There's basically a function you can call. So there's an MPR121.is_touched. And you just pass in the number of a pin. So there are 0 to 11. There are 12 total pins. They're numbered 0 to 11 on the outside here. And you can just pass in which pin. So, I can check, is pin 0 touched? And that returns false. And then if I put my finger on pin 0, it's kind of at the end there. You can see the board actually lights up. There's a little light that lit up on there. Now if I call that, it's true. So that's kind of cool. And I take my finger away, and it's false again. And I touch it, and it's true again like that. So that's a pretty easy way to detect a single pin, whether it's touched. And by the way, too, this might not be the final interface for this library. We might kind of change this over to have some properties and other things. But just for now, this is the current state of this library. So that's pretty simple. You can pretty much do everything you want just with that is touched. But there's one other way that you can read the state of all of the touch inputs. So if you wanted to check, are any of the pins touched, or are multiple pins touched, you could call is touched for each of the 12 pins, and that's actually what this simple test example does. So it has a main loop, and it loops through all 12 pins right here and just calls is touched for each of them. But there's a little bit more efficient way that you can do this. So you can call this .touched function, and this will return a value back. So this returns a 12-bit number, and each bit represents one of the inputs. So bit 0 is input 0, bit 1 is input 1, all the way down to bit 11, which is the 11th input on this board. And if one of those inputs is touched, it will have a 1 value, and if one of the inputs is not touched, it will have a 0 value. So for example, if I touch like all of the inputs, I just put my finger on everything, let's call MPR121.touched, that's giving me a value of 63, and that's basically the maximum value. So if I look at the bit value, so in Python, if you want to have a bit literal, which means I want to specify each of the bits in a value, so I can say like 1, 0, 1, 0, 1, 1, 1, something like that. So let's just say like, let's do all 12 of these are 1s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the bit literal value for all 12 inputs turned on. That gives me value 4095. So I guess I didn't have all of them touched in that case. It's a little bit hard for me to get my finger on all of these. So we'll see if I can get a value. I got a few more touched. It's almost there. But you can see as I touch more of them, some of these pins change. And I'm trying to remember if there's an easy way to convert a Python number into a binary string. I don't think MicroPython has a way that I remember right now to do that. But you can test and see, is a pin touched in this touched value by just looking at that bit position to see if it's set. So for example, let's say MPR121.touched. Now to test if a bit is set, you can usually use the Boolean AND operation. So you want to AND this with a value. So let's say if maybe the second input, so input number 1, so not input number 0, but input number 1. So that would be the bit value 10. So if I see input 1 is touched, then this value should be greater than 0. So if I'm basically testing here, so what's going to happen is it's going to call that MPR121.touched function. That's going to return back a 12-bit value where each bit represents whether one of those inputs is touched. And then I'm going to do the Boolean AND operation where I AND it against the bit literal value 1, 0. So that's going to check to see, is the second bit set? So this second bit right there, because the way the Boolean AND works, any value on the right side here that's set to a 1, any of these bits that's set to a 1, if it's also set to a 1 on the left side, then it will come across and it will be a positive value. If it's not set on the left side, but it is set on the right side here, it's still going to come across as a 0. So it's not still going to come, it's going to come across as a 0. So I'll get a 0 value. Basically, it's going to tell me that it's not touched. So this is kind of an interesting way, but this is typically how you test if a bit is set within a value like this. So I can call this right now. It tells me false, but if I put my finger on input 1 like that, then I get a value true like that. So I can test that, and I can test multiple values with that. So if I want to test if, both, well, this is going to tell me, is either value 0 or 1 set. If either 0 or 1 are set, then this value is going to be greater than 0, like this. So, right now it's false, and if I touch them, then it's true. And then let's make this more interesting. So let's set this up to like something like this. So this is value, let's see. So if value either 0 or, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, yeah. So if 0 or 7 are touched, then this should return true. So right now nothing's touched. Now I'm going to touch number 7. So let's see what happens. So that's true. And then I'm going to touch number 0 down here, and that's also true. And then if I touch something in the middle, looks like I was also touching number 7 a little bit. So it's a little bit hard for me to touch this without breaking out some of the pins, but you can see it's false when nothing's clearly touching it. So that's an efficient way. This is kind of nice in that if you want to check multiple pins, you can call this touched function, get the value back that gives you the state of all the pins at that point in time, and then look for each of the bits that you care about. And then that's a little bit faster because when you use that isTouched function that we saw before, that actually has to make a call to the chip using the I2C protocol, so it's a little bit slow. And if you're doing that in a loop and you're trying to test a lot of pins at once, it's going to take a little bit of time and it might be a little bit too slow for you. So the touched function is kind of handy to have there to use. Okay, so that's basically the simple test example. And I guess just for completeness, I'll show running it. So like I said, download this file onto your computer, and then you can use a tool like Ampy to run it against your board. And in the guide, I link to Ampy and how to use it. But basically, in this example, like I said, make sure to modify the example so that it's set up for either the ESP8266 or the SAMD21 board. By default, it's assuming the SAMD21 board since it's using the native I/O module right here. So I have this in this directory, the simpletest.py, and I'm going to set my Ampy port environment variable to my board name. This is just so I don't have to specify the -- port option to Ampy, but there's no harm, and you can also specify that if you need. And I'm going to Ampy run. Now -n is an option you want to specify because that tells Ampy to run the script but not wait for any output. It's just going to run it and then immediately come back. And then I want to run that simpletest.py. So it's running the simple test, and I'm going to open up the serial terminal again. And so now when I touch some of the inputs, you can see it basically prints out, hey, you touched an input. And it's only telling me when I touch, doesn't tell me when I release, but I could detect that. Like, it's just a simple script right now that's just detecting this. But that's pretty simple and easy. So that's how you detect when something's touched. And I'll close this out. And then, like I mentioned, this code is a simple example that's just looping through and just calling that isTouched function for each of the 12 inputs. And then it just sleeps for a quarter of a second, so it just tests 4 times a second all of the inputs and prints out a message when it detects that one of them is touched. So that's pretty simple, and with that you can do some powerful things. So there's another example in here, this piano.py. So this is a little bit more interesting example. So let's wire this one up. And like I said, I have these spoons right here, and I think this will make a fun example of a more kind of interactive piano device. Rather than touching these little pins right here, I'm going to make it so when I touch the electric spoons, then we'll be able to play some tones. Now, one thing we need to do for this, though, is I need some kind of sound output. And so this is actually a good way. I'll go through how to use a PWM piezo buzzer with CircuitPython. And this would also work with MicroPython. The syntax is going to be a little bit different, but the basic idea of using a pulse width modulated output to drive a little piezo buzzer is going to be the same between these. So first I'm going to close out, I'm closed out of the serial terminal, and then I'm going to disconnect my board real quickly. So I'm just going to pull off the power and the ground connections and then the serial connections. I'm going to move the MPR121 over to another little breadboard that I have right here, just because I already have everything wired up. I didn't want to spend 10 minutes wiring up spoons to alligator clips. That would not make the most interesting YouTube content, I imagine. Okay, so I'm going to plug this back in, and I just want to make sure I get it lined up the right way with the ground pin in the right location. So yeah, that's where I've got it, and that's where I had it before. Now the first thing I'll do before I wire up the MPR121 again, I'm going to go through this little thing. So this is a piezo buzzer. So you might be able to see it's just a little component. It has two leads, like an LED. There are two wires that come out of it. They don't have any special length. So an LED has a short lead and a long lead. This just has two leads, and it doesn't even matter. There's no polarity to this device. It's basically a tiny little speaker, but it's not actually technically the same technology as a speaker. A speaker has a magnet and a moving coil. This actually has a crystal, and when you apply voltage at a certain frequency to that crystal, it'll vibrate, and that can vibrate a little diaphragm in there, which is kind of like the way a speaker works. With a speaker, you just have a magnet and a coil. Like the magnet moves this big cone up and down by changing an electromagnet. This is similar but simpler, so that you don't have this electromagnet in there. You just have this piezo crystal. When you apply voltage to it, it increases or decreases in size. And if you apply a voltage that changes over time with a certain frequency, then it's going to vibrate at a certain frequency. And that vibration can move a little diaphragm effectively like a speaker cone. And that's going to produce sound output out of here. So if you send a signal into this that changes at a certain frequency, like 440 times a second, that's going to produce a tone that you can hear with your ear at that frequency. So it's a really simple, easy way to add sounds or tones to your project. And the nice thing is, you don't need a lot of power to drive these little piezos, so you don't need like a big amplifier. Whereas if you're using a speaker cone and a speaker coil, you usually have to have an amplifier that's supplying a lot more current to it, a lot more voltage. Whereas this can just be powered directly off of the 3 volts or the 5 volts from your development board. So you'll need one of these, and I'll put a link in the description. These are like literally just a few cents. It's a piezo buzzer is all that you need for this. And to wire it up to your board, it's really easy. So one of the wires you connect to ground, and then the other wire you connect to a PWM output on your board. And so you're going to need to look at your board's documentation. On the feather boards, it's kind of nice. We have a little squiggly line next to the digital inputs that support the pulse width modulation output. So if I look at input 9 on this board, there's a little squiggly line next to it, or tilde. And so if you want to use one of those pins to connect to the other wire on your piezo buzzer. So I'm just going to plug this piezo into the breadboard so that it's crossing 2 of the lines there. Now this black wire is connected to one side of the piezo, and this red wire is connected to the other side. And so what I'm going to do is connect this black wire to ground, and actually I'm going to do this by adding another wire right next to it. So let's connect that to the ground of my board right there. And then the other wire on the piezo buzzer I'm going to connect to input number 9, like I mentioned. So that's one of the inputs that has a little squiggly line next to it on my SAMD21 board right there. So I've just wired up my piezo buzzer, and let's test it out in CircuitPython. So I'm going to open up the REPL again. And to use the piezo buzzer in CircuitPython, so this is different between MicroPython. So if you're using MicroPython, look at the MicroPython documentation for your board. It's basically in the machine module. There's a PWM class, and it differs between the ESP8266 and the Pi board. So you're going to need to look at your board to see the difference. In CircuitPython, it's all the same between ESP8266 and the SAMD21 board. But on CircuitPython, so you want to import the board module and then import the native I/O module. And by the way, too, there's a nice little reference that I'll link to. This is for CircuitPython. In the native I/O module, this talks about the PWM out class, which is what we're going to use. And so this tells you exactly how to use this class. So what I want to do is I want to make my buzzer as an instance of native.io.pwm out. And then this needs to take in the pin that the PWM buzzer is connected to. So that's board.d9, the digital 9 pin, this red wire. And again, it has to have a little squiggly line to support the PWM output. And then there are a few parameters that you want to specify here. So there's a duty cycle parameter. So this specifies what duty cycle this should be set to when it's initialized. And so the duty cycle is what % of the time this pulse width modulation signal is on versus off. And it's a percent, but it's not specified in like a 100% value. It's actually a 16-bit value. I believe it's 16-bit. Yeah, 16-bit value. So this is basically a value that goes from 1 to 32,768, or 767 actually. And so the closer it is to 32,767, the larger the duty cycle. So if you want a 50% or exactly halfway duty cycle, then you want a half 16-bit value, which would be like 15,000 something. I'll show you an easy way to compute that in a second here. So let's just start with a duty cycle of 0, which means that it's totally off. Like there's nothing, there's no signal changing. It's all a flatline 0 signal. So start with that. You can also set a frequency for this PWM output. And for this, let's set 440. So this is a value in hertz, which is how many times that this signal changes per second. It's a sine wave. It's just going up. Well, it's not technically a sine wave, but it's a value that goes on and off 440 times a second. You know, I could have a value like if I want to do 1,000 times a second. But since I'm making something that I want to hear with my ear, I want to match the frequency of a tone that you might play with a musical instrument. And so 440 is like an A tone. I believe it's an A, or maybe it's a C. It's been a long time since I've had music classes and things, but this is the frequency of a tone that you'll be able to hear. So that's what I want. And then there's one other thing that you probably want to set. This is an optional parameter, but variable underscore frequency equals true. This will let me change the frequency later. By default, you can't change the frequency unless you specify this variable frequency equals true. So just make sure to specify this if you're going to change the frequency, which I do want to show how to change frequency. And when I have the piano demo set up, I need to change frequency because each of these different spoons represents a different tone or a different frequency that it needs to play. Okay, so do that. Nothing happens because the duty cycle is 0. But now let's set the duty cycle. If I set this equal to, so I want to set a 50% duty cycle because that means that my signal is going to be on for half the time and then it's going to drop down to off for half the time. And that's going to repeat over and over. So it's on, off, on, off. And if you think of that over time, it's on, off, just over and over. It's up, down, up, down, up, down, which is kind of like a sine wave. It's actually a square wave. So it's, you know, it's not going to be like a really nice smooth tone, but that's good enough to vibrate that little piezo crystal, which is going to produce sound waves that I'll be able to hear with my ear. So to set that to a 50% duty cycle, I want to set it to a value that's half of the maximum 16-bit value. Easy way to do that is take 2 to the power of 15. So just set it to 2 star star 15. In Python, the star star just means go to the integer power of this. So I'm going to do that. And you might be able to hear there's a tone that's playing. So that's an A tone. And I can change the frequency. I can say buzzer.frequency equals, let's say 400. So this is going to be a slightly lower frequency. So it should sound a little lower. So let's see what happens when I press enter. So you see it changed a little bit, went down. Let's go to like 300, so a really low tone. So see, a little bit lower like that. And then if I want to turn it off, I can just set the duty cycle back to 0. And that turns it off. It's not moving that signal up and down anymore. And then if I wanted to turn it back on, it remembers the previous frequency. So I go back to that low note and then turn it back off. So that's pretty simple and pretty straightforward. Again, the piezo buzzer, it's very simple to connect. You don't need an amplifier or anything. Easy way to get a tone like this that you can adjust the frequency of. You can't really adjust the volume, unfortunately, because, you know, again, like you're just sending this on-off signal. You don't really have a concept of, you know, only half volume or half as loud. And so it kind of comes down to your piezo. Like a really big piezo buzzer can be really loud, and a small one might not be as loud. So, you know, controlling volume is a little bit harder there. So but it's just an easy way to get like a basic thing. You know, if you had a device and you wanted it to give you some feedback, you know, maybe there's no display, but it's got some buttons and you want to know when you press something. A little buzzer like this is an easy thing to add, and then just play a little beep, you know, a little 440 hertz tone that says, yep, you know, I got that input from the device. Okay, so that's how I connected up the buzzer. And now let's look at this Fruit demo. So, or the, not Fruit demo, so Fruit Orchestra is the kind of the canonical example of the capacitive touch, where you have a bunch of pieces of fruit and you can connect up little alligator clips. But I was kind of thinking, you know, okay, that's such a played out demo. Everyone, you know, if every demo of capacitive touch is using fruit, then you know, what can we do that's a little bit different? So I was trying to think about, you know, some people like to play the spoons, and I cannot do this. I have no idea how you play the spoons. You're supposed to like hold them a certain way and then like click them like this. But I thought a fun little thing is, because, you know, spoons and silverware are conductive, and so that's easy to detect capacitive touch if I just connect an alligator clip to this. And then it made me kind of think, okay, well, there was this seminal moment in history. I'll put a link to this. This was in July 1965 when Bob Dylan at the Newport Folk Festival kind of blew everyone away by switching from acoustic to electric guitar. So this was maybe like the day the world changed, and after that, electric guitar kind of took over all of the rock and pop music of the day. And so a lot of people look back with fond memories, some people with not so fond memories, but for better or worse, Bob Dylan changed the world by plugging in his guitar and going from acoustic to electric. So I thought, why not take the spoons and let's make electric spoons. So we're going to electrify these spoons and detect when you touch them, and we'll play tones. So we're not going to actually be like amplifying the sound of, you know, the spoons. Not really sure how you play these things, to be honest. But these are still electric spoons, and that when I touch these spoons, it's going to play different tones on that piezo buzzer. And so, like I mentioned, there's actually an example in the Circuit Playground, or the MPR121 library for the CircuitPython module, and it's this piano.py module. So open this up, and I have it open in this text editor already. And at the top, you also need to change, like the other example, this little bit of code. If you're running on the ESP8266, you need to uncomment this line right here like that, and then comment out this line because you need to use the correct module. But otherwise, that's all that you need to change to make this run. And then before I get too far into this, I need to reconnect my MPR121 I2C connection to my board. So let me just do that. I'm going to connect the, not that side, let's connect, make sure I get a good connection. There we go. The SDA line, and then the SCL line. So there's SDA, and then there's SCL. So let's connect that. So there we go. Okay, cool. So I just have my board connected again. Okay, so in this script, let's go and just run it. So I'm going to exit out of here, and in this directory, I have that piano.py file. So let's do ampy run. I'm not going to use the -n option right now, just because I'm going to let it run, and then I can press Control-C to stop running it, basically. So let's do ampy run piano.py. This is nice in that it'll tell me if there's an error. Just because I reconnected it, I want to make sure if it fails because the connection's bad, that I know, and then I see that. Oh, see, it couldn't find it. So the little SDA line on this board right now, unfortunately, is not making a good connection. Oh, it's not connected actually because I forgot there's one other wire. I need the VN, the voltage input wire. So let me connect that to 3.3 volts, and then the VN on my MPR121. There we go. So now let's see, when I run this, I will hopefully not get an error back. Okay, oh, see, I'm not getting a good response. So I know that my wiring is probably a little bit suspect on here. And let me just make sure I've got everything connected. Yeah, I'm just gonna hold those down a little bit while I run this. So let's see. Okay, that looks like that's probably okay. Okay, so that's running. And now when it's running, let's see what happens when I touch a spoon. Hey, you might hear a tone playing. That's kind of cool. As I touch each spoon, you can hear that it plays a different tone right here. So, and it's pretty fast. I mean, you know, you can, now it only plays one tone at a time. You don't have polyphony of multiple notes being played on here, but you know, you can go through and touch these. And that's pretty quick and pretty cool. These are the electric spoons. So, okay, I'm going to stop this. It's actually still running. You can see it's still running. If you really want to stop it, open up the screen and press Control C, and then that will interrupt it, and that'll stop the script from running in that case. So let's just look at the code real quick, and I'll show you what I changed to make this example work. So in this example, at the top I have some configuration. So if your buzzer is connected to a different pin, you need to change this buzzer pin variable. I'm using the D9, digital input 9, or digital IO number 9. And then the tone on and the tone off duty cycle values. These are the duty cycle values I was just talking about. I just made these variables so that it's easier to change these. If you want, you could experiment and try different values. But you know, to get a tone, you need to have like at least a 50% duty cycle. You could use probably a smaller duty cycle, but experiment and see what happens. But these are generally values you don't want to change. And then the note frequency array right here, this is how I define what frequency to play when a specific input is touched. So like this spoon right here is input 0, and so it would play a 261 hertz tone, which is a middle C note. And I saw that from this Arduino sketch. It has a little table right here that says here's a C tone that's 261 hertz, and it goes through all of these. So that's what I did in this table. So I can look up and see, okay, you know, spoon number 5, so 1, 2, 3, 4, 5. So this spoon right here is a G, and so that should be 392 hertz. And then the next one is 440, and then the last one right here is 493. Now I set the rest of these to 0 just because I don't have anything else connected to the rest of the pins, but I could add some extra spoons. You know, you could have more than 7 notes if you want right here. You know, I could set like 550 or something like that inside of here, but 0 just means that there's no tone that will be played if that input is touched right here. So you know, you can experiment with these and try different values. Like try like, you know, put a 1 in front of all these to make these like thousands, you know, a lot higher of a tone. So I don't know, let's try that. I'm going to save that. And then let's run that one again, and let's see what happens. So, oh, I don't hear anything. I just hear some clicking. So I think what's happening there is that frequency is probably too fast for the piezo to vibrate and make a sound that I can hear. So let's see. Let's Control C, stop out of that. So okay, so maybe that's a little bit too high of a value, but let's add 100 to all of these. So let's say like 3, 3, 4, 4, 4, 5, 5. And so this should be a little bit higher of a tone. So when I do that, so you can see a little bit higher tone. So that's kind of cool. So neat. It's just fun to play with, and I like making these spoons. You know, these big things that you can interact with and touch. And it's, you know, it's just as easy as connecting a little alligator clip to something. It's something has to be conductive, but it's cool. I mean, you know, go wild with this. You can have like pieces of aluminum foil. Oops. Oh, so this is because I ran without the -n option. Ampy is sitting there waiting for my script to finish. My script never finishes because there's an infinite loop in it, and so eventually Ampy times out. If you want to get around this, run with the -n option like I showed before, and then that just tells Ampy to not wait around for any of the outputs, inputs, and things like that. But anyways, like I was saying, so you know, it's really fun. It's cool to make these interactive things like this. So anyways, though, let's just finish looking at the code for this. So the next bits of code, I create the I2C bus and the MPR121 class, just like I showed in the previous example. And then here's where I set up the piezo buzzer, or the PWM output. And just like I showed before, setting the duty cycle, I set it initially off. The frequency really doesn't matter to what I initially set it, because I'm only going to change the frequency based on what I see someone touching. And then variable frequency equals true. That just means that I'll let you change the frequency later on this buzzer object. Now the main loop is everything that runs continuously in this sketch. And basically what I'm doing is, in this sketch, I'm using that touched function that I talked about before. So it's a fast way to get the state of all 12 of the inputs. And my the rough logic for this loop is that I look for a change in my inputs. So before I start the loop, I get an initial reading of my touch input state. And then every time my loop starts, at the very top of it, I grab a new state. I call it current. So I just see, you know, what's the state of all 12 of my inputs, and then I compare it to my last state. And if there's any difference, if that value differs in any way, you know, if one of those bits is turned off when it was turned on before, then those values are going to be completely different. You know, then this check is going to be true right here. So I'll be able to tell that something changed. You know, either you were touching something and you released it, or you weren't touching anything and you touched something else. You know, so now that state changes. And when I detect that, I basically say, okay, let's just turn everything off. Because, you know, I know, like, you know, you might have removed your hand, and so let's just go back into a known state where everything's turned off. So I set my duty cycle to the tone off duty cycle. And then I want to go through and see, are any of the bits set in the current touch state? And so I go through all 12 of the bits, and then here's where I'm checking for each bit individually. Is it set? And it's doing that check that I was showing before. You know, I'm just using a bit shift operator, this left kind of syntax right here, to just move this bit over one position and check and see. I use the Boolean AND operator against my current touch state, and if it's greater than 0, then I know that input was touched, and I'll print out a little message when that happens. And then I'm not totally done yet, because I want to look up, well, what frequency is associated with that note that was touched. So let's go look in this note frequencies table or array. And so I look up, so like if input number 5 is touched, it's going to give me a value of 540. Or if input number 10 is touched for some reason, it's going to give me a value of 0. And so I want to look and see if my frequency is not 0, because you can't set a 0 frequency. We throw an error in this case, so I just ignore anything with a 0 frequency. So that's these inputs right here. These are unused, so these won't do anything. But if I get a value that's not 0, you know, like 449 for input number 3, then that's going to pass this check right here, and that's where I'll set the buzzer frequency, and I'll set the duty cycle. I'll set this to the on duty cycle. And so that's going to cause it to start playing that sound. And that's all that I do basically in this loop, is I just check through all 12 of those inputs right here. And then when I'm done with that check, I just update my state so that what was my current state is now saved as my last state. I delay for 1/10 of a second just to let CircuitPython do any other processing that it might need to do. And then I go back to the top of the loop, and so I update my new current state, and I check against what was my last state to see, was there any change? And if there was, I go through and apply all this logic again. So I turn off all the sounds, check all the bits to see what's set, and then set the frequency appropriately. So that's how it's detecting all these changes. And it's pretty cool how fast it is. You know, it's just being able to touch these. Oops, I just disconnected this one on accident. So let me reconnect that one. There we go. So that's pretty cool. Oops, looks like I lost this one right there. It's not detecting super well. Sometimes you have to be careful about making sure that you touch it and get a good connection to your finger, because it's got to change the capacitance. And the things that you have connected to, you also need to make sure that that they're somewhat conductive, that they can detect capacitive changes. But that's it. That's all there is to these couple demos that I wanted to show. So this is how to use the MPR121 capacitive touch sensing breakout. You know, this is a really cool little breakout that you can use with any board that supports I2C, and you can use it with Python and CircuitPython now. So this will make some really great demos and cool, fun, interactive things. You know, like I was saying before, you know, I made the electric spoons right here. So this could be another seminal day in history. This could be, you know, just like Bob Dylan plugged in his electric guitar. This is the day Tony D plugged in his spoons and created the electric spoons that might have just changed music history. So remember this day. This is March 24th, 2017. But so that's one example. You could connect pieces of fruit to this. So, you know, have a banana, an apple, a pear, and you touch those, and that makes a really cool interactive demo. Really neat thing that John Park did was with the Circuit Playground board, not using Python, but using Arduino, he had his DJ controller where, using conductive ink, you can draw shapes with conductive ink onto a piece of cardboard and then hook up alligator clips to those conductive parts of ink. And when you touch them, that will change the capacitance, and you'll be able to detect that. And so I could do that also here. I could make the CircuitPython version of the conductive DJ controller. He had a really cool demo. You hook it up to DJ software so that you can like play sound effects and do loops and control, like make a song basically with it. But you know, the electric spoons are a little bit simpler. They just play little piezo buzzer tones like this. And that's all you get for the electric spoons, at least version 1 of the electric spoons. You know, this is, maybe someone could take this and run with it and make a much more advanced electric spoon, maybe that plays samples or sound effects or things. So, okay, so if folks have questions, maybe throw them into the chat. Let's see. Someone was saying, oh, can the duty cycle be given in hex? Yeah, you could totally specify the duty cycle in hex. And so I'll show you real quick how to do that. So if I just cancel out of this, so basically, you know, if you're saying, like, let's say some foo is your duty cycle, you know, you can say, okay, I want a duty cycle of 2 to the power 15. So that gives me this value. I could also specify a hex value. So foo equals, in Python, the way you specify hex is you do 0x, so that, and then that tells Python you're going to specify a hex literal, and then you just specify the hex value as, you know, either 0 through 1 or 0 through 9 or A through F. So if I wanted the same value in hex, I'm trying to remember what that would be. I think it would be like, what is it, like 1000 1111. That would be, no, that's too many. I'm trying to think. Let's see, because that's 1 byte, so this would be 2 bytes. So that should be the same value. Oh no, it's not it. All right, well, this is embarrassing. Embedded math is failing me, but you can see that's a value, or like if I want to say foo equals OXFF, that's going to be 255. So you can specify them in hex is what I'm getting at here. Just use OX. There are other ways, like I was saying, there's the binary literal, so you can do like 1100, that gives you some value. And there's also an octal literal in Python, and for that one you do 00, and then like either one's octal values, which I forget, it's been so long since I've specified octal stuff. I'm pretty sure that's the way, or I think the way octal works is you just specify a 0 and then values in front of it. I don't know, like let's see, 1 2 3 4 5 6 7 8, I don't know, something like that. Maybe that's not it. I don't know, I can't remember exactly what the octal one is, but it's pretty rare to use it. Obviously I haven't used it much since I don't remember what it is. So okay, so I think that was it. I think that was all the questions. So I will jump back to the main shot right here. So thanks a lot for watching. That was how to use the MPR121 capacitive touch breakout with CircuitPython. So I walked through how to install the module. There's a guide that you should check out. It's linked in the description below when this goes up on YouTube, so you can follow that guide. It tells you what hardware you need. And we looked at a couple demos. So a simple example of how to detect if an input is touched on that board, and then the electric spoons, where I showed how to make a more complete example of capacitive touch sensing, where you can play tones based on touching things like spoons that you have connected there. So that's it. Thanks a lot for watching. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos. Check out twitch.tv/Adafruit. That's where I stream things live. I like to do a stream every Friday to show off some interesting stuff. We've been on a roll with a lot of different CircuitPython stuff. Last week I did a cool NeoPixel color synthesis demo that was kind of the start of what it will probably be a multi-part series. So maybe next week we'll pick up on the next part of that series and look at how to do cool animations with NeoPixels. And I want to get to a point where you can make fun and interesting organic animations without having to understand a ton of math and a ton of code. Something that, like a cosplayer, you know, if you want to have like a cool glowy costume effect or something, maybe I can make some cool primitive color synthesis functions and things you can use to make that easier. So stay tuned for more fun stuff from Adafruit. Until next time, thanks a lot for watching. So this is Tony from Adafruit. I'll see you later. Bye.